There is a lot of kind of fun math problems that come from reversing the order of integration. There is some applications, there's times where really you have to reverse the order of integration in order to solve the problem, but also there's just kind of like a lot of neat math puzzlers, things that you could only solve using this kind of trick. So let's practice the reverse laser beam method. So I've set up a double integral here, and we're asked to kind of go backwards and recover what the region was. All right, so the first thing that I do is I'm graphing all the boundary curves. So the curves are y is equal to x squared and y is equal to x cubed. So let me try to graph those. So y equals x squared. All right, here we go. I've got to draw a parabola. Up close. Let me try again. It's going to take me 50 tries. All right, whatever. That's the best I can do. All right, and then y is equal to x cubed is going to look something like this. All right, that's the best that I can do. So in this setup, since this is dy, remember I am drawing a laser beam that is parallel to the y-axis. So this is going to be a vertical laser beam, and this is the enter, and this is the exit. So if I drew a vertical laser beam up right there, this is where it would enter, and that is where it would exit. So I am doing all of that region right there. And now, should I color in this piece over here? No, I shouldn't, because I am only using the vertical laser beams that go in between 0 and 1. Okay, so that's the thought process that I use to decide that the region is kind of this crescent moon shape there. Let me just clean up this picture. Now I'm going to try to reverse the order of integration. So it started off as being dy and then dx, and so I reversed it, so now it's dx and then dy. So there's the region, and what I'm going to need to do is draw a horizontal laser beam this time, because I'm doing dx first. So this enters the region at the inside function here is the parabola, and the outside function is the degree 3 equation there. So that means this enters the region at x equals the parabola first. So this is going to be x equals the square root of y, and it's going to exit at the degree 3 function. So this will be x is equal to the cube root of y. And then I just need to ask, which y's am I going to get a laser beam that intersects this region? You can see there's dy coming second, so these should be y numbers. So those are going to be all the y's from y equals 0 up to y equals 1. And just to be clear, this y value is that one right there, and this x value is that one right there. So this problem had symmetry, so they were both the same, but in the bottom one, those ones are y values, and the top one, those are x values. Okay, so that's the process that you use to reverse the order of integration. You just sketch the region, you use the reverse laser beams to figure out which region you're talking about, and then you just go through the process of setting it up. I have another example that's kind of interesting, because you could actually only solve this problem after reversing the order of integration. So let's look at that. Here's the example. We're asked to find the total mass of a region, and this region has variable density, and the density is e to the x squared. So if you see this in math problems, I just want to let the cat out of the bag what's going on here. This e to the negative x squared, that function is the bell curve, the classic Gaussian bell curve, which is a really important function, especially in probability and statistics and stuff. And so what's the issue? Well, the issue is that this e to the x squared does not have an antiderivative in terms of elementary functions. There just isn't one. We just don't have the name of a function that when you take the derivative, it gives you e to the x squared. So, the way this problem is set up right now, we are legitimately stuck. There's no way to come up with an antiderivative. So I don't know, I just can't work out the answer. But observe that if I reversed this order of integration, if it was dy first, then e to the x squared is a constant. So, that it's easy to find antiderivatives of constants. So, maybe if we reverse this order of integration, we will be able to work out this integral. I think it's going to work. Let's give it a shot. Okay, so I've just sketched the curves that we're dealing with here. The first one is x is equal to y over 2. So that's a line, and the slope of the line is 2 there. So that's that line. And then the other one is x is equal to the square root of the natural log of 10. Okay, that's kind of an ugly number, but it's just a number, and the equation x equals a number is a vertical line. So that's what I've drawn right here. X is equal to the square root of the natural log of 10. Now, if you look at this like laser beam setup here, if I drew a horizontal line, a laser beam kind of parallel to the x-axis, then it would enter at the slanted line and exit at the vertical line. So this is the region that we're talking about. Okay, great. So now all I need to do is try to set up this integral again, but using the reverse order. All right, so I'm ready to set up my integral here. I have reversed the order of integration. Now it's dy and then dx, and this is the region that I'm dealing with. So I'm doing dy first, so I'm going to draw a vertical line, a laser beam that goes up and down. And this is going to enter at y is equal to 0, and it's going to exit at that line. So that's the line y is equal to 2x. Okay, now which x values do I actually get a line inside the region? Okay, this one over here, that doesn't give me a line inside the region. And that one over there, that doesn't give me a line inside the region. So all I'm going to need is all the x's between 0 and this vertical line, and that right there is where we got the equation of that vertical line. So it's going to be for all the x's between 0 and the square root of the natural log of 10. Okay, brilliant. Now, maybe I might be able to work out this integral. Okay, so I did it. It's actually really easy now. Look at this. So now for this integral right here, I am integrating with respect to y. So x is just a constant at this part of the problem. So this thing right here is just a constant. So all I'm doing is coming up with an antiderivative of a constant. So an antiderivative of a constant with respect to y is just y times that constant. Okay, and then now I'm just going to plug in my y limits right there. So I'm still going to have this integral out front from 0 to the square root of the natural log of 10. Now, when you plug in 0, it's just going to go away. And then when you plug in 2x, you're going to get 2x e to the x squared dx. And now you can see the stupid smile on my face and the magic that happened in this problem. Now we can solve this with a simple u sub, right? I mean, if u is equal to x squared, then du is 2x dx. So that's it. Brilliant. So this is just going to be e to the x squared, like e to the u, evaluated from 0 to the square root of the natural log of 10. So when you plug in 0, you're going to get 1. When you plug, so this is going to be e to the square root of the natural log of 10 squared minus e to the 0 squared. Okay, so the squared and the square root are going to cancel, and then the e and the natural log are going to cancel. So this is just going to be 10, and then e to the 0 is just 1. So this whole integral works out to be very beautiful, just 9. So there's in the world of math, we consider this a fun kind of problem because here is an example of an integral that we couldn't do the way that it was set up, and then we did this kind of trick where we reversed the order of integration, and then after that, the whole thing just, plays out in a nice, beautiful way. So I am pitching it here as though it is just some kind of like silly little trick, but there are real times in the theory of math that this process is meaningful. So, now you have that under your belt. You've seen it before. So if you ever encounter it again, it won't be quite as much of a mystery.